What are the chances of getting lucky 5 times in a row? And more importantly, can you actually calculate it? You've probably never come across this formula from probability theory, but it actually explains a lot of things happening in your everyday life, from making a streak of free throws in basketball to getting rare drops in games. Today, I'll explain in the simplest way possible how this formula works, where it comes from, and what exactly it allows you to calculate. Let's start with a basic concept in probability: adding probabilities. Imagine there are 5 balls in front of you, and you are allowed to choose 2 of them. Let's say you pick ball number 1 and ball number 4. What is the probability that another person, choosing randomly, picks one of your balls? There are different ways to explain this, but for our purposes, here's a simple way to think about it. The probability of picking ball number 1 is 20%, and the probability of picking ball number 4 is also 20%. So the probability of picking either ball number 1 or ball number 4 is 20% plus 20% is 40%. And the key idea here is the word or, because for us, picking ball number 1 is just as good as picking ball number 4. The addition rule of probability tells us that if events are mutually exclusive, the probability of event A or event B is simply the sum of their probabilities. This rule is quite simple, but I think it is often overlooked. Now let's look at slightly modified example. This time you choose one ball from each of 2 groups. In the first group, you pick ball number 1, and in the second group, you pick ball number 3. What is the probability that another person, choosing randomly, makes the same choices in both groups? Here, things are a bit less obvious. Many people know that you can just multiply the probabilities. 20% times 20% is 4%. But why multiplication? We can think of this as a decision tree. As the first step, the person has 5 possible choices. This creates 5 unique, mutually exclusive paths. After making the first choice, they move to the second group, where they again have 5 options. As you can see on the screen, the tree quickly expands. Each path represents a unique outcome, whether it's 1 and 2 or 3 and 5. All of these outcomes do not overlap, and each endpoint is a possible result. But we are interested in just one specific outcome, 1 and 3. First, let's count the total number of possible outcomes. That's simply 5 times 5 equals 25. So, the probability of choosing exactly the path we want is 1 out of 25, which is 4%. Now let's connect this back to multiplication. Suppose there are A possible choices in the first step and B in the second. If these choices are independent, the second choice does not depend on the first one, then the total number of outcomes is A times B, and the probability of one specific outcome is 1 over A times B. But this is the same as 1 over A multiplied by 1 over B, and that's exactly why we multiply probabilities. In fact, each step narrows down the number of possible outcomes. I know this may feel obvious, but these simple examples become very important once the number of steps grows. Just like before, where we had the OR rule, this is the AND rule. Alright, these basic ideas, plus a bit of math, are enough for us to understand this formula. But what does it actually calculate? Let's say the game gives you 7 loot boxes as a birthday reward. Inside each loot box, there are common, uncommon, rare, epic, and legendary rewards, and we know the probability of getting each type. We are not setting unrealistic expectations, so let's say our goal is to get 3 rare or better rewards. In practice, people usually want at least 3, but we'll come back to that later. For now, we'll focus on getting exactly 3 rewards, just to keep things simple. And this is exactly what the formula allows us to calculate: the probability of that specific outcome. Here's what each part means. P is the probability of getting a successful outcome in a single trial, in our case, getting a rare or better reward from one loot box. N is the total number of trials, the number of loot boxes. K is the number of successful outcomes we want, in our case 3. This formula is called the Bernoulli Formula, named after the Swiss mathematician Jacob Bernoulli. And as I promised, now let's see where this formula actually comes from. To explain the formula, let's go back to our loot box example. Let's start from the simplest case, a single loot box. The probability of getting a reward we care about, let's call it P, is the sum of the probabilities of getting a rare, epic, or legendary item, since any of these outcomes works for us. The probability of getting an unwanted reward is then 1 minus P. Notice that both of these terms already appear in the formula. Great! Now that we understand the simplest case, let's go back to 7 loot boxes. What is the probability of one specific sequence of outcomes? For example, the first, third, and fourth boxes give us desired reward, while the other 4 do not. Here we can use the AND rule. Since each loot box is independent, we simply multiply the probabilities. This gives us P times 1 minus P times P times P, and so on. If we group the terms, we get P in the power of 3 times 1 minus P in the power of 4. Now let's look back at the formula. It should already look more familiar. We now have powers. Notice that the exponents always add up to the total number of trials n. In our case, 3 plus 4 equals 7. This makes sense. If 3 outcomes are successful, the remaining 4 must be failures. Here's an important observation. No matter how we rearrange the order of outcomes, the probability remains the same. That is because each case contains the same number of successes and failures, and multiplication does not depend on order. Now we can move to the last, and probably the least intuitive part of the formula. Some of you may recognize this as the binomial coefficient, but instead of using that definition, let's derive it directly from our example. Since we've grouped all successful outcomes into a single probability P, let's also group them visually. We'll mark all successful outcomes in purple and all unsuccessful ones in gray. Now look at these two cases. What is the difference between them? They differ only in the order of outcomes. From a probability standpoint, these are different outcomes, because each loot box generates its result independently. However, they share one important property. Their probabilities are exactly the same. As we've seen, each of these cases has probability of P in the power of 3 times 1 minus P in the power of 4. Now, let's recall the OR rule. Since any of these cases works for us, we can add their probabilities together to get the total probability. So all we need now is to count how many such cases there are. Let's call this number Q, the number of favorable arrangements. So the total probability becomes Q times P in the power of 3 times 1 minus P in the power of 4. Now, comparing this with the formula, we see that this coefficient is exactly the number of ways we can get 3 successful outcomes out of 7. So how do we calculate it? Let's approach this from a combinatorics perspective. We have 7 loot boxes and 3 successful rewards to place. Imagine you're the game, assigning rewards to boxes. We already know there will be exactly 3 successful outcomes. We're not thinking about probabilities here, just about counting arrangements. First, you place one successful reward. You have 7 choices to place it. Then you place the second one. For this one, you have only 6 choices left because of the first choice. Then the third, 5 positions left. So the total number of ways to place them is 7 times 6 times 5. But there is one problem. We've counted the same arrangement multiple times, because we treated each success as if it were different. We only care whether it was a success or not. So all successful outcomes are indistinguishable for us, and we need to divide by the number of ways to arrange them. It is 3 factorial, or 3 times 2 times 1. Finally, we get this formula, and this gives us the number of ways to get 3 successes among 7 trials. All that's left now is to write this in a general form. To derive the general form of the formula, we can make a few transformations. We replace all specific numbers with variables, apply the properties of factorials, and arrive at the final expression. For our example, the formula gives us the following result. So the probability of getting exactly 3 desired rewards is 22.7%. It's not hard to see that to get at least 3 rewards, we need to sum the corresponding terms, which gives us 35.3%. Now you understand how the Bernoulli formula works. But the main takeaway isn't memorizing the formula itself, it's understanding how independent repeated random events behave. You don't actually need to remember the formula. There are plenty of tools where you can just plug in the numbers. Even Excel has a built-in function. What really matters is understanding the logic, knowing what k, n, and p represent, and how to use them to compute the probabilities you care about. Please like and subscribe if you enjoyed the video, and leave a comment about what do you want to see as the next topic.